124 light-years from here, orbiting a dim red star in the constellation Leo. Something is happening that might change everything we thought we knew about being alone. Scientists using the James Webb Space Telescope have detected chemicals in a distant atmosphere that on Earth are made only by living things. The confidence level sits at 99.7%. That leaves just a 3 in 1,000 chance this could be random noise. The planet is called this ocean world, and its atmosphere is screaming with molecules that marine algae pump into our own skies. If you enjoy content like this, consider hitting that subscribe button. Prepare yourselves. What comes next will challenge every assumption you have about life in the universe. Picture this. A planet crosses in front of its star. For a few hours, a tiny fraction of starlight passes through the atmosphere of that distant world before reaching us. Inside that light are secrets. The James Webb Space Telescope captures this light and splits it into a rainbow of colors. Each chemical in that atmosphere absorbs specific wavelengths. Methane eats up certain reds. Carbon dioxide swallows particular infrareds. Water vapor leaves its own signature. Scientists call this transmission spectroscopy, and it works like reading a barcode written in starlight. This technique is confirmed science, used successfully on dozens of worlds. When the planet transits its star, Webb detects the drop in brightness. But more importantly, it catches the fingerprints left behind by every molecule floating in that alien sky. The process is precise. The telescope sits 1 million miles from Earth, far beyond our atmosphere, where nothing interferes with its view. Its mirrors are coated in gold to capture infrared light, the wavelengths where these molecular signatures shine brightest. Here is what makes this revolutionary. Webb can detect chemicals at concentrations as low as parts per million. On Earth, that would be like finding a single drop of ink in a swimming pool. The data comes as graphs showing dips and peaks at specific wavelengths. Each dip represents a molecule absorbing light. Match the pattern, identify the chemical. Methane has 4 characteristic absorption bands. Carbon dioxide shows 2 strong features. Water leaves 3 distinct marks. The James Webb Space Telescope uses 2 instruments for this work. One is called the Near-Infrared Spectrograph. It looks at wavelengths between 0.6 and 5.3 microns. The other is the Mid-Infrared Instrument, examining wavelengths from 5 to 28 microns. Together, they create a complete picture of what chemicals float in distant atmospheres. When scientists aimed Webb at this ocean world, they expected to see methane and carbon dioxide. Both had been detected before using the Hubble Space Telescope, though the older instruments struggled with precision. What they found instead made them check their instruments 3 times. The graph showed absorption features that matched only one thing: dimethyl sulfide, or possibly its chemical cousin, dimethyl disulfide. Both molecules share similar spectral signatures in the observed range. The signal appeared at wavelengths between 4 and 5.2 microns. Multiple absorption bands lined up perfectly with laboratory measurements of these sulfur compounds. The strength of the signal indicated concentrations exceeding 10 parts per million. For reference, Earth's atmosphere contains these molecules at less than 1 part per billion. Something on this world was producing them at thousands of times the rate we see here. But what comes next is even stranger. Scientists ran the observations twice using different instruments. Both times, the same signature appeared. The probability this occurred by random chance sits at 0.3%. That is 3 sigma certainty in statistical terms. Not quite enough to declare victory, but far beyond coincidence. To reach 5 sigma, the gold standard for scientific discovery, they need just 2 or 3 more observation windows. Those could happen within the next year. The next question becomes obvious. What could possibly create these molecules in such staggering amounts? On our planet, dimethyl sulfide has only one confirmed source, life. Specifically, tiny organisms floating in the ocean called phytoplankton. These microscopic algae produce a compound called dimethyl sulfoniopropanate as they grow. When they die, or when bacteria break them down, this compound transforms into dimethyl sulfide. The gas escapes into the atmosphere, and you can smell it. Walk along any beach, and that sharp, slightly unpleasant scent in the air. That is dimethyl sulfide. Scientists have searched for decades for any non-biological way to make this molecule in planetary atmospheres. They have found nothing that works at meaningful scales. Laboratory experiments can create trace amounts through reactions between methane and hydrogen sulfide under specific conditions, but these pathways are inefficient. They require exact ratios of ingredients and produce dimethyl sulfide at concentrations far below what we observe on Earth, let alone what Webb detected on this distant world. Here is why this matters. Most biosignature gases have problems. Methane can come from volcanoes. Oxygen can be created when ultraviolet light splits water molecules. Phosphine might form in violent storms on gas giants. Each of these has at least one known abiotic pathway that muddies interpretation. Dimethyl sulfide and its cousin dimethyl disulfide stand apart. Their chemistry requires specific biological pathways that no known geological process can replicate at high concentrations. The molecule has a short lifetime. In Earth's atmosphere, dimethyl sulfide breaks down within days. Sunlight tears it apart. Oxygen attacks it. Hydroxyl radicals destroy it. This means any dimethyl sulfide we detect must be continuously replenished. On Earth, phytoplankton bloom and die in cycles, pumping fresh supplies into the air. The fact that we can measure it at all proves something is making it constantly. Now imagine finding this gas on another world at 10,000 times Earth's concentration. The math becomes unavoidable. Whatever source exists, there must be incredibly powerful. Some process is generating dimethyl sulfide or dimethyl disulfide faster than chemistry can destroy it. On Earth, our oceans teem with trillions upon trillions of phytoplankton working around the clock. To produce the concentrations Webb detected would require life on a scale difficult to comprehend. Theoretical work published before Webb's observations predicted this exact scenario. Scientists modeling hypothetical ocean worlds with hydrogen atmospheres calculated that if life existed there, dimethyl sulfide would accumulate to much higher levels than on Earth. The hydrogen atmosphere would slow down the destruction pathways. Microbes could thrive in warm oceans beneath. Their waste products would build up over time. The predictions matched observations almost perfectly. This is a theory supported by models, not yet confirmed fact. But the alignment between prediction and observation makes scientists cautiously optimistic. One researcher at Cambridge stated that given everything known about this planet, an ocean world teeming with life represents the scenario that best fits the data. But caution remains the watchword. The next step involves ruling out every alternative explanation, no matter how unlikely. What if something else we have never considered could make these molecules? When scientists say they have 99.7% confidence, they are talking about statistics. Specifically, they mean the signal they detected has only a 0.3% chance of being random noise. In the language of statistics, this is called 3 sigma certainty. Picture flipping a coin. Get 10 heads in a row, and you might suspect the coin is weighted. That is roughly 3 sigma. Get 20 heads in a row, and you would be certain. That is 5 sigma. The gold standard for claiming scientific discovery sits at 5 sigma. At that level, the probability of error drops below 0.00006%. Particle physicists used 5 sigma when announcing the Higgs boson. Astronomers used it when confirming gravitational waves. For something as profound as detecting alien life, nothing less will suffice. Right now, this discovery sits at 3 sigma, exciting but not conclusive. Here is how they calculated this. The James Webb Space Telescope collected data showing absorption features at specific wavelengths. Scientists then compared this data against models. One model assumed dimethyl sulfide or dimethyl disulfide present in the atmosphere. Another model assumed these molecules were absent. The model with the sulfur compounds fit the data significantly better. Statistical tests revealed that the probability of getting this good a fit by chance, if the molecules were not actually there, equals 0.3%. But chance is not the only concern. Systematic errors can fool instruments. Maybe the telescope's calibration drifted slightly. Maybe thermal noise created false signals. Maybe the star itself has unusual properties that mimic the signature of dimethyl sulfide. Scientists spent months checking for these possibilities. They used two different instruments on Webb. Both saw the same signal. They examined observations of other planets to ensure the signature was unique. They modeled dozens of alternative atmospheric compositions. Nothing else fit as well. To reach 5 sigma, they need more data. Each observation window lasts about 8 hours as the planet crosses its star. They have used 2 windows so far. Scientists estimate they need 2 or 3 more. That means another 16 to 24 hours of telescope time spread across multiple transits. The planet completes an orbit every 33 days, so opportunities arise frequently. But Webb is the most oversubscribed telescope in history. Thousands of astronomers compete for time. Getting approval requires a rigorous selection process. The lead researcher stated they have formally applied for additional observation time. A review panel will decide whether the science justifies the cost. If approved, confirmation could come within 12 months. That timeline puts us potentially 1 year away from knowing whether we have detected alien life. 1 year away from answering humanity's oldest question: are we alone? But here is what makes this moment electric. Even at 3 sigma, even with uncertainty remaining, we have crossed a threshold. For the first time in history, we have data from another world that is easier to explain with life than without it. That has never happened before. What makes this world special enough to produce such a signal? The planet orbits a star called a red dwarf. These stars are smaller, cooler, and dimmer than our Sunday. This particular red dwarf has a temperature of about 3,184 degrees Celsius. Our sun burns at 5,500 degrees Celsius. The red dwarf contains only 45% of our sun's radius. Less mass, less heat, less light. But here is the trick. The planet orbits much closer to compensate. Earth sits 93 million miles from the Sunday. This ocean world orbits just 13 million miles from its star. That puts it 167 times closer than Earth relative to its star's size. Distance matters more than you might think. The intensity of starlight follows the inverse square law. Double your distance and you receive 1/4 the light. Move 10 times closer and you get 100 times more light. This planet orbits so close that despite its star's dimness, it receives roughly the same amount of energy Earth does. Scientists call this the habitable zone. It is the region around any star where a planet with the right atmosphere could maintain liquid water on its surface. For our Sun, that zone spans from about 90 million to about 140 million miles. For red dwarfs, the habitable zone sits much closer, sometimes just a few million miles out. This confirmed by decades of observations and climate modeling. Temperature is not just about distance. Atmospheres change everything. A planet with a thick atmosphere traps heat through the greenhouse effect. Carbon dioxide and methane are particularly good at this. Water vapor helps too. The right mix can keep a world warm even far from its star. Venus demonstrates this principle gone wrong. Despite being closer to the Sun than Earth, Venus would be cooler if not for its crushing carbon dioxide atmosphere. Instead, surface temperatures reach 470 degrees Celsius. This ocean world has a hydrogen-rich atmosphere. Hydrogen is less efficient at trapping heat than carbon dioxide, but it makes up for this with sheer volume. Models suggest the atmosphere might represent up to 6% of the planet's total mass. For comparison, Earth's atmosphere is less than 1/1,000,000th of our planet's mass. That much hydrogen creates a strong greenhouse effect, even with lower efficiency per molecule. But here comes a complication. The same closeness that allows liquid water also brings danger. Red dwarfs are violent stars. They produce powerful flares, sudden bursts of radiation, and charged particles that blast nearby planets. These flares can strip away atmospheres over millions of years. They bathe planets in ultraviolet and X-ray radiation that destroys complex molecules and sterilizes surfaces. Yet this world appears to have retained its atmosphere. Observations show abundant hydrogen, methane, and carbon dioxide. If the star were constantly stripping atmosphere away, we would see signs of atmospheric loss. The presence of heavy molecules suggests the planet has held onto its envelope for a long time. Perhaps its strong gravity helps. Perhaps the atmosphere is thick enough to weather the storms. Or perhaps we are witnessing something special, a planet in a brief window before its atmosphere disappears. The star itself is estimated to be 2.4 billion years old. Earth is 4.5 billion years old. This star system is roughly half our age, young enough that the planet may still be geologically active, old enough that any life would have had time to evolve. What happens when you combine all these factors with the strangest feature of this world? One orbit takes 33 Earth days. That means a year there lasts just over a month. Imagine celebrating your birthday 33 times faster. You would be over 1,000 years old by the time you reached your 30th birthday by Earth standards. But this speed has consequences that ripple through every aspect of the planet's behavior. First, consider seasons. On Earth, seasons occur because our axis tilts 23 degrees. When the northern hemisphere tilts toward the sun, we get summer. 6 months later, we tilt away and get winter. This ocean world likely has minimal axial tilt, meaning seasons would not happen the way we experience them. Instead, any climate variation comes from the orbit itself. Here is where things get interesting. The orbit is not perfectly circular. Scientists measure this using a number called eccentricity. Earth's orbit has an eccentricity of 0.017, nearly a perfect circle. This ocean world has an eccentricity of about 0.09, over 5 times more elliptical. This is confirmed through precise measurements of orbital timing. That means the distance from the star changes significantly throughout each orbit. At the closest point, the planet sits about 12% nearer to the star than at the farthest point. That might not sound like much, but the inverse square law amplifies this difference. The planet receives about 43% more starlight at closest approach compared to farthest distance. Imagine if Earth's climate swung that wildly every few weeks. Temperatures would spike and crash in cycles. Any water on the surface would face constant freeze-thaw cycles. This creates a stability problem. Life as we know it requires stable temperatures. Extreme swings make it hard for complex chemistry to establish itself. Water might freeze at one part of the orbit, then boil at another. Organisms would need to survive both extremes within a single month. On Earth, extremophile bacteria can handle wide temperature ranges. Some thrive in boiling hot springs. Others survive in Antarctic ice. But asking organisms to handle both extremes on a monthly schedule is a different challenge entirely. Yet the dimethyl sulfide signal persists. If life exists there, it has adapted to this chaotic rhythm. Perhaps the thick hydrogen atmosphere acts as a buffer, smoothing out temperature extremes. Perhaps life retreats to deeper waters during temperature swings, waiting for conditions to stabilize. Perhaps the oceans themselves store enough heat to prevent wild fluctuation. There is another problem with fast orbits. When a planet orbits this close to its star, gravitational forces become intense. The star pulls harder on the near side of the planet than the far side. Over millions of years, this difference in pull creates tidal forces that slow the planet's rotation. Eventually, the planet becomes tidally locked. One side always faces the star in permanent daylight. The other side faces away in eternal darkness. Scientists suspect this ocean world is tidally locked, though this remains unconfirmed. If true, the day side would be scorching hot. The night side would be frozen solid. Only a narrow twilight band between the two hemispheres might maintain temperatures suitable for liquid water. Wind would howl across this boundary as hot air from the day side rushes to fill the frigid night side. Weather patterns would be unlike anything we see on Earth. But what if the thick hydrogen atmosphere changes the game? Computer models show that a dense atmosphere can transport heat from day side to night side efficiently. This could create more habitable conditions across larger portions of the surface. Without seeing the planet directly, scientists can only estimate these effects. What they know for certain is that this world is nothing like Earth in terms of day-night cycles. How does a planet 2.5 times Earth's size maintain conditions that might support life? The planet has a radius 2.6 times larger than Earth. That makes it massive. Its volume is over 17 times ours. If you could stand on the surface, assuming there is a surface, gravity would crush you at about 2.5 times Earth's strength. Every step would feel like carrying another copy of yourself on your back. This is confirmed through precise measurements of the planet's mass and size derived from orbital mechanics. But size creates a problem. Planets this large usually do not look like Earth. They look like Neptune. Our solar system has 4 rocky planets and 4 gas giants, with nothing in between. This ocean world sits exactly in that gap. Scientists call planets like this sub-Neptunes. They are bigger than Earth, but smaller than Neptune. We have discovered thousands of them around other stars, but we have none in our own system to study up close. Here is the mystery. We do not know what sub-Neptunes are made of. Are they rocky planets that captured huge atmospheres? Are they icy worlds like Neptune that never grew large enough to become full gas giants? Are they something else entirely? A type of planet that does not exist in our solar system? The answer determines whether life could survive there. The density offers clues. Earth has a density of 5.5 grams per cubic centimeter. That is because we are mostly iron and rock. Neptune has a density of 1.6 grams per cubic centimeter. That is because Neptune is mostly water, ammonia, and methane ices wrapped in hydrogen and helium gas. This ocean world has a density of 2.67 grams per cubic centimeter, right between Earth and Neptune. One possibility is this. The planet has a rocky core, perhaps 3 to 4 times Earth's mass. Above that sits a mantle of high-pressure ice. Not the ice you find in your freezer, but ice that forms under extreme pressure and stays solid even at high temperatures. Above that might be liquid water, and above that, a thick atmosphere of hydrogen and helium. This structure is purely theoretical, a model built from mass and density measurements. No one knows for sure. This model leads to the concept of Haitian worlds. The word combines hydrogen and ocean. The idea suggests planets with hydrogen atmospheres and liquid water surfaces could be habitable despite being much larger than Earth. The hydrogen atmosphere would trap heat through greenhouse warming. The liquid water provides a medium for life. Microbes could float in these oceans, just like phytoplankton float in Earth's seas. But critics point out problems with this picture. At the surface pressures expected on such a large planet, water might not stay liquid. It might exist in a supercritical state, where the distinction between liquid and gas breaks down. Imagine water that flows like liquid, but has the density of steam. That state begins above 374 degrees Celsius and above 221 times Earth's atmospheric pressure. If the surface temperature or pressure exceeds these thresholds, liquid oceans cannot exist. Some scientists argue this world is too hot. Climate models suggest that with its thick hydrogen atmosphere and the amount of starlight it receives, surface temperatures could exceed 500 degrees Celsius. At that temperature, any water would exist as supercritical fluid or steam. The surface might be molten rock, a magma ocean wrapped in a hydrogen blanket. If so, the dimethyl sulfide signal needs a different explanation, but other models tell a different story. They suggest that if clouds form in the upper atmosphere, those clouds could reflect enough starlight to keep the surface cool. An albedo, the measure of reflectivity, above 90% could maintain liquid water. Whether such clouds can form remains uncertain. The chemistry of hydrogen-rich atmospheres makes cloud formation different than on Earth. What makes the absence of certain molecules a crucial clue? Earth's oceans contain about 25 trillion phytoplankton. These microscopic organisms drift in the sunlit surface waters, using photosynthesis to turn carbon dioxide and sunlight into energy. They produce roughly half the oxygen we breathe. They form the base of the oceanic food chain, and they make dimethyl sulfide when you visit the beach. That distinctive smell in the air comes largely from these tiny beings. Phytoplankton create a compound called dimethyl sulfoniopropanate to regulate salt balance in their cells. It acts as an osmolyte, helping them deal with the saltiness of seawater. When the phytoplankton die, or when bacteria attack them, enzymes break down this compound. One of the breakdown products is dimethyl sulfide. The gas escapes into the atmosphere at a rate of about 100 million tons per year globally. This is confirmed science, measured directly through atmospheric sampling and satellite observations. The molecule does not last long. Hydroxyl radicals in the atmosphere attack it within days. Sunlight breaks it apart. It oxidizes into sulfur dioxide, then sulfuric acid, which forms tiny particles. These particles seed clouds. More clouds mean more sunlight reflected back to space, cooling the planet. Some scientists propose this creates a feedback loop. Warmer oceans produce more phytoplankton. More phytoplankton make more dimethyl sulfide. More dimethyl sulfide creates more clouds. More clouds cool the planet. This hypothesis remains unproven but widely discussed. Now, consider what it means to detect dimethyl sulfide on another world. The signal requires continuous production. Something must churn out the molecule faster than chemistry destroys it. On Earth, the combined efforts of trillions upon trillions of phytoplankton cells barely maintain atmospheric concentrations of 1 part per billion. To reach 10 parts per million, the concentration observed on this ocean world requires a production rate 10,000 times higher. What could possibly do that? One option is simply more phytoplankton. If the oceans there contain vastly more microbial life per unit volume than Earth's oceans, the math works. But why would that be? Perhaps the combination of hydrogen atmosphere and liquid water creates ideal conditions for microbial blooms. Perhaps nutrients are more abundant. Perhaps the lack of predators allows populations to explode unchecked. Another option involves different chemistry. Perhaps organisms there produce dimethyl sulfide directly rather than as a byproduct. On Earth, phytoplankton make dimethyl sulfoniopropanate for one reason, and dimethyl sulfide happens as a side effect. On another world, life might use dimethyl sulfide as a signaling molecule, a metabolic product, or even a waste product of energy generation. Different evolutionary pressures could lead to different uses for the same molecule. There is also the question of bacterial contribution. On Earth, bacteria play a huge role in converting dimethyl sulfoniopropanate into dimethyl sulfide. Certain bacterial species specialize in this transformation. An ocean full of these bacteria, feasting on organic matter, could produce enormous quantities. The dimethyl disulfide, detected alongside dimethyl sulfide, supports this. On Earth, dimethyl disulfide comes primarily from bacterial metabolism, not phytoplankton directly. The smell these molecules produce is strong and unpleasant. At high concentrations, dimethyl sulfide reeks of rotting vegetables or decaying seaweed. Some describe it as garlicky or sulfurous. If you could somehow visit this ocean world and breathe the atmosphere, assuming the hydrogen did not kill you first, the stench would be overwhelming. Imagine standing downwind of a massive algae bloom covering millions of square miles, all releasing dimethyl sulfide at once. That is what this planet's air might smell like. But smell is the least interesting aspect. The real question is what this molecule tells us about the possibility of life. On Earth, we have searched for decades for any non-biological way to make dimethyl sulfide at meaningful concentrations. We have found nothing. Every pathway requires living cells. If the same holds true on this distant world, then we are detecting life's chemical signature written in starlight. How could concentrations be 10,000 times higher than Earth's? Earth's atmosphere contains dimethyl sulfide at less than 1 part per billion by volume. Sample air from above the ocean and you will find it, but barely. The molecule breaks down quickly. Its lifetime in our atmosphere averages about 1 day. This is confirmed through careful atmospheric chemistry studies. Sunlight attacks it. Hydroxyl radicals tear it apart. Oxygen converts it into sulfur dioxide. The only reason we detect it at all is because phytoplankton constantly replenish the supply. This ocean world shows concentrations exceeding 10 parts per million. That is more than 10,000 times higher. To put this in perspective, imagine if carbon dioxide on Earth suddenly jumped from 400 parts per million to over 4 million parts per million. The entire planet would become uninhabitable within days. But dimethyl sulfide is not carbon dioxide. It does not drive greenhouse warming the same way. Its primary effect is chemical, not thermal. What could explain such high concentrations? One possibility involves the hydrogen atmosphere itself. On Earth, oxygen dominates our atmosphere at 21%. Oxygen is highly reactive. It destroys dimethyl sulfide efficiently. This ocean world has a hydrogen atmosphere with minimal oxygen. Hydrogen is less reactive toward dimethyl sulfide. The destruction pathways that work on Earth might not work there. The molecule could last weeks or months instead of days. Longer lifetime means less production needed to maintain high concentrations. If dimethyl sulfide survives 10 times longer, you need only 1/10 the production rate to achieve the same concentration. If it survives 100 times longer, you need 1/100th the production rate. Scientists modeling this ocean world calculated that in a hydrogen atmosphere with high carbon dioxide and low oxygen, dimethyl sulfide could persist much longer than on Earth. This is theoretical, but based on established atmospheric chemistry principles. But even accounting for longer lifetime, the numbers are staggering. 10 parts per million requires enormous production. One research team estimated you would need a biogenic flux, the rate at which organisms produce the gas, thousands of times greater than Earth's oceans provide. That suggests either far more life per unit volume or far more efficient dimethyl sulfide production pathways, or both. Here is where the carbon dioxide connection matters. Webb detected about 1% carbon dioxide in this planet's atmosphere. That is 25 times higher than Earth's 400 parts per million. High carbon dioxide levels can affect how organisms metabolize sulfur compounds. Some bacteria on Earth use carbon dioxide in their metabolic pathways. Perhaps on this ocean world, the abundance of carbon dioxide drives different biochemical pathways that produce more dimethyl sulfide per cell. There is another factor. Temperature affects chemical reaction rates. Warmer water means faster metabolism. If the oceans there are warmer than Earth's, organisms might grow faster, reproduce faster, and produce waste products faster. The average temperature of Earth's oceans is about 3.5 degrees Celsius. Models suggest this ocean world surface could range from 10 degrees to over 50 degrees Celsius, depending on cloud cover and greenhouse strength. At 30 degrees Celsius, biological processes run several times faster than at 3 degrees Celsius. Combine all these factors: a hydrogen atmosphere that slows dimethyl sulfide destruction, high carbon dioxide driving altered metabolic pathways, warm oceans accelerating biological processes, potentially higher biomass density than Earth's oceans. The multiplication of effects could explain why concentrations are so much higher. Each factor alone might provide a 2 times or 5 times boost. Together, they multiply, not add. 2 times, 5 times, 3 times 4 equals 120 times. Add a few more factors, and you reach 10,000 times. But critics ask a different question. What if the high concentrations prove the signal is not biological? What if there is an abiotic, non-living chemical pathway that produces dimethyl sulfide efficiently in hydrogen atmospheres? Laboratory experiments have explored this. Scientists mixed methane, hydrogen sulfide, and exposed them to ultraviolet light. They created trace amounts of dimethyl sulfide. But trace amounts mean parts per billion, not parts per million. The experiments fall short by factors of thousands. How does a molecule with such a short lifetime survive long enough to be detected? Every molecule has a lifetime, the average time it exists before breaking apart. For dimethyl sulfide in Earth's atmosphere, that lifetime is brutally short. One study measured it at 24 hours. Another found 48 hours. The variation depends on local conditions like sunlight intensity, temperature, and the abundance of oxidizing chemicals. But the conclusion remains the same. Dimethyl sulfide does not last long. This is confirmed science, replicated in numerous studies. 3 main processes destroy dimethyl sulfide on Earth. First, hydroxyl radicals attack it. These radicals are molecular fragments with unpaired electrons, making them incredibly reactive. They form when ultraviolet light breaks apart water molecules in the upper atmosphere. Once formed, hydroxyl radicals attack almost any organic molecule they encounter. They grab hydrogen atoms, breaking chemical bonds. Dimethyl sulfide has 6 hydrogen atoms ripe for taking. Second, oxygen directly reacts with dimethyl sulfide. The reaction is slower than with hydroxyl radicals, but still significant. Oxygen combines with the sulfur atom, creating sulfur dioxide as the first step. Eventually, this pathway leads to sulfuric acid formation. That is why burning sulfur-containing fossil fuels creates acid rain. The sulfur becomes sulfur dioxide, then sulfuric acid, then falls as precipitation. The same chemistry happens to dimethyl sulfide naturally in the atmosphere. Third, sunlight itself can break dimethyl sulfide apart. Photodissociation occurs when a photon carries enough energy to snap chemical bonds. For dimethyl sulfide, ultraviolet wavelengths between 200 and 300 nanometers do the damage. These wavelengths carry enough punch to break the carbon-sulfur bonds holding the molecule together. The pieces fly apart and recombine with other atmospheric chemicals. Now consider a hydrogen atmosphere. Hydroxyl radicals still form, but less efficiently. Hydrogen atmospheres contain less water vapor to break apart. Less water vapor means fewer hydroxyl radicals. Fewer radicals means slower destruction of dimethyl sulfide. Models suggest the hydroxyl radical concentration in this ocean world's atmosphere might be 1/10 or 1/100th of Earth's levels. Oxygen presents even more dramatic differences. This ocean world has minimal oxygen. Spectroscopic observations show no detectable oxygen features. That means the direct oxidation pathway that destroys dimethyl sulfide on Earth does not work there. Eliminating one major destruction route automatically extends the molecule's lifetime. Photodissociation still happens. The planet's star puts out ultraviolet light, though red dwarfs emit less UV than our Sun day. The hydrogen atmosphere itself might absorb some UV before it reaches lower altitudes where dimethyl sulfide concentrates. Methane and carbon dioxide also absorb certain UV wavelengths, providing additional shielding. The net effect is that dimethyl sulfide experiences less photochemical stress. Put all this together, and dimethyl sulfide might survive 10 times longer, possibly 100 times longer, than on Earth. Instead of 1 or 2 days, it might last weeks or months. That transforms the production requirements. If you only need to replenish the molecule every few weeks instead of every day, you need much less biological activity to maintain the same atmospheric concentration. A factor of 10 in lifetime reduces production requirements by a factor of 10. But here is the catch. Even with a 100 times longer lifetime, you still need significant production to maintain 10 parts per million. The math is unavoidable. Something on this world generates dimethyl sulfide at rates that dwarf anything we see on Earth. The extended lifetime helps explain how the concentration stays so high, but it does not eliminate the need for a powerful source. Scientists are trying to pin down exact lifetime numbers through detailed atmospheric modeling. They input the observed concentrations of methane, carbon dioxide, and hydrogen. They calculate photochemistry reaction by reaction, tracking how each molecule interacts with others. They estimate UV flux from the star. They model temperature and pressure at different altitudes. The result is a prediction of dimethyl sulfide lifetime under those specific conditions. Early models suggest lifetimes between 10 and 100 days, but uncertainty remains large. What could explain these signals without invoking life at all? Not everyone believes the dimethyl sulfide signal means life. A growing number of scientists point to an alternative explanation. What if this world has no oceans at all? What if the surface is molten rock wrapped in a hydrogen atmosphere? Magma oceans could produce some of the same chemical signatures as living oceans. This alternative explanation comes from detailed climate modeling, published in early 2024. Here is how magma oceans might work. The planet receives substantial starlight despite orbiting a dim red dwarf. A thick hydrogen atmosphere creates a powerful greenhouse effect. Even though hydrogen is not as efficient as carbon dioxide at trapping heat, enough of it creates serious warming. Models suggest surface temperatures could exceed 800 degrees Celsius under these conditions. This is theoretical, based on energy balance calculations and known atmospheric properties. At those temperatures, rock melts. Granite melts around 1,200 degrees Celsius. Basalt melts around 1,100 degrees Celsius. But rocks are complex mixtures. Some minerals melt at lower temperatures. A planetary surface at 800 degrees would not be fully molten, but it could have widespread lava flows, lava lakes, and molten regions covering large fractions of the surface. Picture Io, Jupiter's volcanic moon, but scaled up to 2.5 times Earth's size. Magma interacts with atmospheres in complex ways. Volcanic gases bubble up through molten rock. These gases include water vapor, carbon dioxide, sulfur dioxide, and hydrogen sulfide. When hydrogen sulfide enters a hydrogen-rich atmosphere, chemistry happens. At high temperatures, hydrogen sulfide can react with carbon-containing molecules to form organic sulfur compounds. Laboratory experiments have demonstrated this. The yields are low, but continuous volcanic outgassing could maintain steady production. One research team ran the numbers. They modeled a planet with a magma surface, a hydrogen atmosphere, and volcanic outgassing rates similar to Earth's most active volcanic periods. Their model produced dimethyl sulfide through abiotic chemistry, but the concentrations fell short by factors of 10 to 100 compared to observations. They could make dimethyl sulfide without life, but not enough of it. The gap suggests biology might still be needed, but it does not rule out enhanced volcanic processes we do not fully understand. There is another clue: ammonia. On Earth, nitrogen-rich atmospheres produce ammonia when lightning or other energy sources combine nitrogen with hydrogen. Ammonia is also produced by life. Many bacteria generate ammonia as a waste product. Models predict that a habitable ocean world should have detectable ammonia, yet observations show none. The absence of ammonia is confirmed through spectroscopic analysis. Magma ocean models explain the missing ammonia naturally. Nitrogen dissolves into molten rock under high pressure. The technical term is nitrogen partitioning into the melt phase. If the surface is molten, atmospheric nitrogen gets absorbed into the magma. This depletes ammonia from the atmosphere. You end up with a planet that has nitrogen locked in the surface rather than floating in the air. This matches observations perfectly. Ocean world models struggle with the missing ammonia. If liquid water exists at the surface, nitrogen should stay in the atmosphere. Ammonia should form through chemical reactions and biological processes. Its absence becomes a puzzle. Some scientists argue that certain metabolic pathways could consume ammonia as fast as it forms, but this requires special conditions. The magma ocean explanation is simpler. It requires no special biology, just basic chemistry. But magma ocean models face their own challenges. They struggle to explain the methane detected in the atmosphere. Methane should not be stable at high temperatures. It breaks down into carbon and hydrogen above about 700 degrees Celsius. To maintain 1% methane in the atmosphere requires either continuous production or cooler temperatures than magma ocean models predict. Either option creates problems for the magma ocean hypothesis. The debate continues. Some scientists favor the magma ocean explanation because it explains missing ammonia. Others favor the ocean world explanation because it explains abundant methane and dimethyl sulfide. Both camps agree more observations are needed. The next round of Webb observations might detect other molecules that settle the question. Certain chemicals would only exist in magma conditions. Others would only exist with liquid water. What if the planet does have water, but the atmosphere is more alien than anyone expected? Hydrogen dominates this planet's atmosphere. Spectroscopic observations confirm this. The absorption features, the way starlight gets filtered, all point to massive amounts of hydrogen and helium. This creates a fundamental problem for life as we know it. Earth's atmosphere is 78% nitrogen, 21% oxygen, and just trace amounts of other gases. No hydrogen at all at ground level. Hydrogen is too light. It escapes Earth's gravity and drifts into space. But this ocean world is more massive. Its stronger gravity holds onto hydrogen. Life on Earth evolved in a nitrogen-oxygen environment. Our proteins, our enzymes, our cellular machinery all assume certain atmospheric chemistry. Oxygen serves as the final electron acceptor in respiration, the process that powers most complex life. Without oxygen, you are limited to anaerobic metabolism. That works fine for bacteria and some simple organisms, but complex multicellular life, the kind that builds civilizations, needs oxygen or something equivalent. A hydrogen atmosphere changes everything. Hydrogen is not just inert like nitrogen. It actively participates in chemistry. It reduces other molecules, the opposite of oxidation. This affects what chemical reactions are possible. Some reactions that proceed easily in oxygen-rich atmospheres become difficult or impossible in hydrogen-rich ones. Other reactions that never happen on Earth become favorable. But here is the surprising part. Life might not only tolerate hydrogen atmospheres, but thrive in them. Recent laboratory experiments tested whether Earth microbes could survive in pure hydrogen. The results shocked researchers. Bacteria and yeast that normally never encounter hydrogen grew just fine when exposed to 100% hydrogen atmospheres. This is confirmed experimental data published in peer-reviewed journals. The organisms did not grow faster, but they did not die either. They adapted. Hydrogen offers metabolic opportunities. Some bacteria on Earth use hydrogen as an energy source. They combine hydrogen with carbon dioxide to make methane, gaining energy in the process. These methanogens live in deep-sea vents, in swamps, in the guts of animals. They prove that hydrogen-based metabolism works. On a planet with abundant atmospheric hydrogen, these metabolic pathways might dominate. The question becomes whether complex organisms can evolve in such environments. On Earth, the jump from single-cell to multicellular life coincided with rising oxygen levels. The Great Oxidation Event, 2.4 billion years ago, filled our atmosphere with oxygen from photosynthetic bacteria. Within a few 100 million years, complex life emerged. Correlation does not prove causation, but the timing is suggestive. Some scientists argue that oxygen's high energy density makes it ideal for powering complex life. Others argue that any sufficiently energetic metabolism could work. Hydrogen metabolism provides less energy per reaction than oxygen metabolism, but it still provides energy. Maybe complex life evolves more slowly in hydrogen atmospheres. Maybe it takes different forms. Maybe it never gets beyond microbial colonies. We do not know because we have only one example of life to study. The hydrogen atmosphere on this ocean world likely came from the planet's formation. When planets form, they accrete gas from the surrounding nebula. Large planets capture more gas. If a planet grows massive enough quickly enough, it captures huge amounts of hydrogen and helium before the star's radiation blows away the nebula. This ocean world probably captured several Earth masses of hydrogen during formation. This is theoretical but well supported by planet formation models. Over time, atmospheric escape slowly strips away hydrogen. High-energy particles from the star knock hydrogen atoms out of the upper atmosphere. They gain enough speed to overcome the planet's gravity and drift away. Red dwarf stars produce frequent flares that accelerate this process. Yet this world retained its hydrogen atmosphere over billions of years. That suggests either the planet is young or the atmosphere is thick enough to weather the losses. The thickness matters for habitability. A thin hydrogen atmosphere would not trap much heat. A thick one creates extreme greenhouse warming. The challenge is finding the right balance. Too thin and any liquid water freezes. Too thick and surface pressures become crushing. Models suggest this planet sits near the edge of habitability. Small changes in atmospheric mass could tip it from habitable to uninhabitable. Why do some scientists think this world resembles Neptune more than Earth? Neptune has a radius about 4 times larger than Earth. Its mass is 17 times ours. Its atmosphere is mostly hydrogen and helium, with about 2% methane. Deep below the atmosphere lies a mantle of water, ammonia, and methane ices. Deeper still, a rocky core, perhaps slightly larger than Earth. Neptune is not a gas giant like Jupiter. It is an ice giant, dominated by volatile compounds rather than hydrogen gas. This ocean world shares many characteristics with Neptune, despite being smaller. The density tells part of the story. Neptune's density sits at 1.6 grams per cubic centimeter. This ocean world measures 2.67 grams per cubic centimeter. Earth is 5.5 grams per cubic centimeter. The progression is clear. This planet falls between Neptune and Earth in density. Simple calculations show it must contain less rock than Earth and more rock than Neptune. But what fills the gap? Interior structure models provide answers. Scientists input the observed mass and radius. They add constraints from planetary science. Rocky materials have certain densities. Water ice under pressure has a different density. Hydrogen gas compressed to high pressure has yet another density. By testing different combinations, scientists narrow down plausible interior structures. This is theoretical but grounded in physics and chemistry, established through laboratory experiments and quantum mechanics. Most models converge on a similar picture: a rocky core 1 to 3 times Earth's mass. Above that, a thick mantle of high-pressure ice and possibly liquid water. This layer might be 1,000 to 2,000 miles thick. Above that, a hydrogen-helium atmosphere thousands of miles deep, gradually thinning as altitude increases. This structure looks nothing like Earth. It looks like a small Neptune with slightly more rock and less gas. If this picture is correct, the planet has no solid surface in any meaningful sense. Descending through the atmosphere, you would find increasing pressure and temperature. Eventually, the hydrogen becomes so dense it behaves like liquid. Deeper still, the ice mantle begins. But there is no sharp boundary, no place where you could land a spaceship. The transition from atmosphere to ice happens gradually over hundreds of miles. This is how Neptune works. Observations suggest this ocean world works similarly, but this interpretation conflicts with the dimethyl sulfide detection. Neptune does not produce dimethyl sulfide. Its atmosphere contains methane, ethane, acetylene, and other hydrocarbons. No sulfur-based organic molecules have ever been detected there. If this distant world resembles Neptune, why does it show chemistry Neptune lacks? One possibility is a liquid water layer sandwiched between the ice mantle and the hydrogen atmosphere. At certain depths, pressure and temperature could allow liquid water to exist. This water would not be in contact with space or air like Earth's oceans. It would be trapped beneath thousands of miles of hydrogen. But it could still host life. Microbes floating in this buried ocean could produce dimethyl sulfide. The gas would bubble up through the atmosphere, reaching altitudes where telescopes detect it. Critics point out problems with this scenario. How would life start in a buried ocean? On Earth, life likely began in shallow pools or near hydrothermal vents, places where energy and chemicals concentrate. A buried ocean lacks these features. Energy would be scarce. Nutrients would be limited. Starting life in such conditions seems implausible. But once started, perhaps through some unknown mechanism, life might spread and thrive. Another issue is methane. Neptune has 2% methane. This ocean world has 1%. On Neptune, methane comes from the planet's interior, released through convection and atmospheric mixing. If this world resembles Neptune, its methane might have the same source. But ocean world models explain methane differently. They propose biological production, with methanogens creating methane from hydrogen and carbon dioxide. Both explanations fit the observations, making it hard to distinguish between them. The debate boils down to whether this planet has a surface and oceans, or lacks both. Spectroscopy tells us what chemicals exist in the atmosphere. It does not directly reveal what lies beneath. We infer surface conditions from atmospheric composition, but inferences can be wrong. Multiple explanations can fit the same data. Breaking this degeneracy requires additional observations that probe deeper into the planet's nature. What happens when scientists examine the mysterious absence of a crucial atmospheric component? The concept of Haitian worlds emerged in 2021 from theoretical work led by researchers at Cambridge. They asked a simple question: can planets larger than Earth but smaller than Neptune host liquid water oceans despite having hydrogen atmospheres? Conventional wisdom said no. Hydrogen atmospheres were thought to create runaway greenhouse effects, making surfaces too hot, but detailed modeling revealed a different possibility. This is theoretical work based on established climate physics. The key is cloud formation. High in the atmosphere, water vapor can condense into clouds. These clouds reflect starlight back into space before it heats the surface. If enough clouds form, they could keep the planet cool despite a strong greenhouse effect lower in the atmosphere. The sweet spot exists when cloud cover reaches about 50 to 70% of the planet. Too little cloud and the surface overheats. Too much cloud and starlight cannot penetrate to support photosynthesis or heat the water. Haitian worlds would have surface pressures between 100 and 1,000 times Earth's atmospheric pressure. That sounds crushing, but Earth's oceans already experience such pressures just a few miles down. Life thrives in the deep ocean despite pressures over 1,000 times surface levels. If life can handle those pressures in Earth's oceans, perhaps it could handle them at a Haitian surface where the pressure comes from atmosphere instead of water depth. Temperature is the trickier constraint. Water stays liquid between 0 and 100 degrees Celsius at Earth's surface pressure, but at higher pressures, water stays liquid at higher temperatures. At 100 atmospheres of pressure, water boils at 311 degrees Celsius instead of 100. At 200 atmospheres, the boiling point rises to 365 degrees Celsius. This is confirmed through laboratory pressure-temperature phase diagrams for water. The upper limit comes at the critical point of water. Above 374 degrees Celsius and 221 atmospheres, water enters a supercritical state where liquid and gas phases merge. Supercritical water has bizarre properties. It flows like a gas but dissolves substances like a liquid. It could potentially support life, but life as we know it relies on the distinct properties of liquid water. Going supercritical might make habitability impossible. High-Cian models suggest surface temperatures between 10 and 70 degrees Celsius are possible under the right conditions. That range is compatible with life. Earth's hottest environments, like deep-sea hydrothermal vents, reach over 100 degrees Celsius and host thriving bacterial communities. If High-Cian oceans stay cooler than that, life seems plausible. But establishing those temperatures requires precise balancing of greenhouse warming and cloud cooling. The hydrogen atmosphere serves multiple roles. It provides greenhouse warming to prevent freezing. It protects from harmful space radiation. It offers metabolic fuel for hydrogen-using organisms. But it also blocks ultraviolet light that drives photosynthesis on Earth. High-Cian life might need to adapt to dimmer, redder light that penetrates the atmosphere. Red dwarf stars emit mostly red and infrared light anyway, so this might not be a problem. Nutrient availability poses another challenge. On Earth, continental weathering releases minerals into rivers that flow to oceans. These minerals provide nutrients for marine life. High-Cian worlds might lack continents entirely. Without weathering, how do nutrients reach the ocean? Perhaps volcanic activity on the seafloor releases minerals directly into water. Perhaps the ocean is supplied from below, with chemicals seeping up from the rocky mantle beneath. One intriguing prediction is that High-Cian worlds should show specific atmospheric signatures: high methane levels from biological production, high carbon dioxide from volcanic outgassing or biological respiration, detectable water vapor, and potentially biosignature gases like dimethyl sulfide or methyl chloride. This ocean world matches the predicted pattern almost perfectly. The alignment between prediction and observation is what excites researchers. How might thick atmospheres create stable conditions? Greenhouse effects get a bad reputation. Climate change discussions focus on runaway greenhouse warming as catastrophic. But greenhouse effects are not inherently bad. They are what make Earth habitable in the first place. Without our natural greenhouse effect, Earth's average temperature would be minus 18 degrees Celsius. The oceans would freeze solid. Instead, greenhouse gases keep us at a comfortable plus 15 degrees Celsius. This is basic atmospheric physics, confirmed through decades of measurements. The mechanism is straightforward. Sunlight passes through the atmosphere and warms the surface. The warm surface radiates energy back as infrared light. Greenhouse gases absorb this infrared, trapping heat in the lower atmosphere. The gases eventually re-radiate the energy, but some goes back down toward the surface. This creates a warming effect. More greenhouse gas means more warming. The relationship is not linear, but it is predictable. On Earth, carbon dioxide and water vapor provide most of the greenhouse effect. Methane and nitrous oxide contribute smaller amounts. These gases work because their molecular structures absorb infrared wavelengths. Not all gases do this. Nitrogen and oxygen, which make up most of our atmosphere, are transparent to infrared. They do not contribute to greenhouse warming. Hydrogen and helium are similarly transparent. You need other molecules mixed in. This ocean world's hydrogen atmosphere does not trap much heat directly. but it contains about 1% methane and 1% carbon dioxide. That might not sound like much, but it is enough. Earth's atmosphere contains only 400 parts per million carbon dioxide, which is 0.04%. This distant planet has 25 times more carbon dioxide than Earth. Methane is an even more powerful greenhouse gas than carbon dioxide, molecule for molecule. 1% methane provides serious warming. Here is where hydrogen becomes important. The sheer mass of the hydrogen atmosphere increases the pressure at the surface. Higher pressure means denser air. Denser air holds more heat. It also slows the escape of infrared radiation. Photons trying to leave the planet get absorbed and re-emitted multiple times before finally making it to space. Each absorption-emission cycle delays heat loss. The result is that even though hydrogen itself does not trap infrared well, a thick hydrogen atmosphere still creates significant greenhouse warming through pressure effects alone. Models show that a hydrogen atmosphere containing 1% carbon dioxide and 1% methane can maintain surface temperatures warm enough for liquid water, even on a planet receiving less starlight than Earth. This extends the habitable zone outward from the star. Planets that would be too cold with Earth-like atmospheres become warm enough with hydrogen atmospheres. It flips conventional thinking about where to look for life, but there is a catch. The greenhouse effect must be strong, but not too strong. Venus demonstrates what happens when greenhouse warming goes out of control. Venus receives twice the sunlight Earth does and has a crushing carbon dioxide atmosphere. Surface temperatures reach 470 degrees Celsius, hot enough to melt lead. The greenhouse effect ran away. All water evaporated, creating more greenhouse gas, creating more warming, creating more evaporation. A positive feedback loop with no braking mechanism. This ocean world sits right on the edge. Computer models show that small changes in atmospheric composition or cloud cover could push it into runaway greenhouse territory. If clouds fail to form, surface temperatures spike. Water evaporates, creating more greenhouse warming. Once started, the process might be irreversible. Alternatively, if clouds become too thick, they block too much starlight. Surface temperatures drop, water freezes. Frozen surfaces reflect more light, creating more cooling. Another runaway process, but in the opposite direction. The fact that this planet apparently maintains stable conditions suggests a balancing mechanism. Perhaps biological processes help stabilize climate. On Earth, phytoplankton produce dimethyl sulfide, which seeds clouds. More warming means more phytoplankton. More phytoplankton means more dimethyl sulfide. More dimethyl sulfide means more clouds. More clouds mean more cooling. This negative feedback might prevent runaway warming. The same mechanism could work on this ocean world. If so, life would not just exist there. Life would actively regulate the planet's climate, making it habitable. Why does the absence of ammonia split scientific opinion? Ammonia should be there. Multiple models predict it, yet observations show no trace. This absence has become one of the most debated aspects of this planet's atmosphere. Ammonia is nitrogen and hydrogen combined. Formula written as one nitrogen atom bonded to 3 hydrogen atoms. In a hydrogen-rich atmosphere receiving energy from starlight or lightning, ammonia formation is expected. This is confirmed chemistry, observed in laboratory experiments and in gas giant atmospheres in our solar system. Jupiter has ammonia, so does Saturn, Uranus, and Neptune. Wherever you find hydrogen and nitrogen, together with enough energy to drive reactions, ammonia appears. Spectroscopic observations of these planets show strong ammonia absorption features. No one questions whether ammonia is there. The question is why it is missing from this ocean world when it should be present. One explanation invokes biological consumption. Some bacteria on Earth metabolize ammonia as an energy source. Nitrifying bacteria convert ammonia to nitrite, then nitrate. They gain energy from these reactions. In an ocean full of such bacteria, ammonia could be removed from the atmosphere as fast as it forms. The ocean acts as a sink. Atmospheric ammonia dissolves into water. Bacteria consume it. More atmospheric ammonia dissolves to replace what was consumed. An equilibrium establishes where ammonia concentrations stay near zero. This explanation fits the ocean world hypothesis nicely. It requires life, but life is what the dimethyl sulfide signal suggests anyway. The two pieces of evidence support each other. Biological metabolism explains both the presence of dimethyl sulfide and the absence of ammonia. It creates a self-consistent picture, but it requires assuming life exists, which is what scientists are trying to prove. Circular reasoning becomes a risk. The alternative explanation invokes chemistry without biology. If the surface is molten rock, nitrogen dissolves into the magma. Experimental studies of volcanic systems show that at high temperatures and pressures, nitrogen partitions into melt phases rather than staying in the gas phase. A magma ocean would suck nitrogen out of the atmosphere. Without atmospheric nitrogen, ammonia cannot form. The absence of ammonia becomes evidence for a magma ocean rather than a water ocean. This explanation fits the magma ocean hypothesis nicely. It requires no life. It explains the missing ammonia through straightforward chemistry, but it struggles to explain the dimethyl sulfide. As discussed earlier, magma ocean models can produce small amounts of dimethyl sulfide through abiotic chemistry. Whether they can produce enough remains questionable. The magma ocean hypothesis explains one mystery while struggling with another. There is a third possibility rarely discussed. Maybe the spectroscopic observations simply missed the ammonia. Ammonia has absorption features at specific wavelengths. If those wavelengths were not observed, or if noise obscured the signal, ammonia could be present but undetected. However, the James Webb Space Telescope observed multiple wavelength ranges. The instruments have sufficient sensitivity to detect ammonia at expected concentrations. Multiple research teams analyzed the data independently. All reached the same conclusion: no ammonia. The missing ammonia forces scientists to choose between competing scenarios. Either life consumes it, or magma absorbs it, or some third unknown process removes it. Each choice leads down a different path for understanding this world. Ocean world with life, magma ocean without life, or something entirely unexpected. The scientific community remains split. Some researchers strongly favor the biological explanation. Others lean toward magma oceans. A third group argues the data remains too ambiguous to choose. What they all agree on is that more observations are desperately needed to break the deadlock. Imagine an ocean where every drop of water contains 1,000 times more microbes than Earth's most productive seas. That is what the numbers demand. The dimethyl sulfide concentrations observed require staggering amounts of biological activity. On Earth, phytoplankton float in the sunlit surface waters, about the top 600 feet where light penetrates. Below that, darkness reigns. Photosynthesis stops. On this ocean world, the same depth limit would apply unless something changes the rules. One possibility is simply density. Earth's oceans contain roughly 1 million bacterial cells per milliliter of seawater. That sounds like a lot, until you consider that fertile soil contains 1 billion cells per gram. Ocean water is relatively sparse in microbial life compared to other environments. Perhaps this distant ocean is more like fertile soil, dense bacterial mats floating in the water column, thick biofilms coating every available surface, microbial density 1,000 times higher than Earth's oceans. This is speculation, but the math requires it. Another possibility involves different organisms entirely. On Earth, dimethyl sulfide comes primarily from eukaryotic phytoplankton, organisms with complex cells containing nuclei and organelles. These evolved relatively late in Earth's history, about 2 billion years ago. Before that, simpler bacteria dominated. Perhaps this ocean world hosts bacteria that produce dimethyl sulfide through different metabolic pathways. Bacteria can evolve quickly, adapting to local conditions within thousands of generations. An ocean full of dimethyl sulfide-producing bacteria could generate the observed concentrations. The hydrogen atmosphere opens unique metabolic possibilities. Some Earth bacteria called methanogens combine hydrogen gas with carbon dioxide to produce methane. They gain energy from this reaction. It works well in environments without oxygen. Perhaps similar organisms on this ocean world combine hydrogen with sulfur compounds to produce dimethyl sulfide directly. This would be more efficient than Earth's pathway, where dimethyl sulfide forms as a byproduct rather than a primary metabolic product. Temperature matters too. Warmer water means faster metabolism. Chemical reactions roughly double in speed for every 10 degrees Celsius increase in temperature. If this ocean's surface averages 30 degrees Celsius compared to Earth's 4 degrees, reactions proceed about 8 times faster. 8 times faster metabolism means 8 times more dimethyl sulfide production per cell. Multiply that by higher cell density, and you start reaching the required production rates. There is also the question of evolutionary pressure. On Earth, phytoplankton produce dimethyl sulfoneopropionate to regulate salt balance. The dimethyl sulfide is accidental. But what if organisms on this world use dimethyl sulfide for communication? Bacteria on Earth use chemical signals to coordinate behavior, a process called quorum sensing. When enough bacteria gather in one place, their chemical signals reach threshold concentrations that trigger collective responses. Perhaps dimethyl sulfide serves this function there, with organisms deliberately producing it in large quantities. Energy availability drives biological productivity. On Earth, photosynthesis captures sunlight and converts it to chemical energy that powers the food chain. This ocean world receives similar amounts of starlight as Earth. The red dwarf star emits more red and infrared light compared to our sun's broader spectrum. But some Earth organisms photosynthesize using red light efficiently. Purple bacteria and some cyanobacteria thrive in red-dominated environments. Life there might have adapted similarly. Nutrient availability is equally important. On Earth, upwelling brings nutrients from deep water to the surface, fueling productive regions like the California coast and the waters around Antarctica. Without continents to create coastal upwelling, this ocean world might rely on different mechanisms. Perhaps volcanic activity on the seafloor releases nutrients directly into the water column. Perhaps strong tidal forces from the nearby star create mixing that brings deep nutrients to the surface. Either way, high productivity requires high nutrient supply. But could life even survive the temperature swings this planet experiences? Life on Earth survives astonishing extremes. Bacteria thrive in boiling hot springs at Yellowstone, where water reaches 90 degrees Celsius. Other organisms survive in Antarctic ice at -40 degrees Celsius. Tardigrades, microscopic animals called water bears, can endure temperatures from near absolute zero to 150 degrees Celsius. Life is tougher than most people realize. These extremes are confirmed through direct observation and laboratory testing. But this ocean world might push even beyond Earth's extremes. Climate models show that depending on atmospheric conditions, surface temperatures could range from 10 degrees Celsius to over 70 degrees Celsius. The elliptical orbit causes variations throughout each 33-day year. At closest approach to the star, temperatures spike. At farthest distance, they drop. The difference might exceed 20 degrees Celsius between orbital extremes. Any life there must handle these swings or find ways to avoid them. Earth organisms use several strategies for temperature tolerance. Some enter dormancy during unfavorable conditions. Bacterial spores can survive for thousands of years in suspended animation, waiting for conditions to improve. When temperatures become favorable again, they reactivate and resume growth. Perhaps organisms on this ocean world sporulate during temperature extremes, then bloom during moderate periods. This would create cycles of biological activity synchronized with the orbit. Other organisms use biochemical adaptations. Proteins fold into specific shapes to perform their functions. Temperature affects protein stability. Too hot and proteins unfold, losing function. Too cold and enzymes slow down. But thermophilic organisms, heat-loving bacteria, produce proteins with extra chemical bonds that stabilize structure at high temperatures. Psychrophilic organisms, cold-loving bacteria, use flexible proteins that remain active even when cold. Life on this ocean world might combine both strategies, producing proteins stable across wide temperature ranges. The ocean itself provides buffering. Water has high heat capacity, meaning it takes a lot of energy to change its temperature. Large bodies of water warm slowly and cool slowly. Even if air temperatures swing wildly, ocean temperatures remain more stable. Earth's oceans show daily temperature variations of just 1 or 2 degrees at the surface, despite air temperature swings of 10 or 20 degrees. An ocean on this distant world would similarly buffer temperature changes, smoothing out the orbital variations. Depth offers another refuge. On Earth, surface waters fluctuate in temperature with seasons and weather. Deeper waters remain stable year-round. Below about 600 feet, ocean temperature barely changes. It stays around 4 degrees Celsius in most places, regardless of what happens at the surface. Life could retreat to stable deep water during temperature extremes, then rise to the productive surface layer during favorable periods. Vertical migration is common in Earth's oceans. Many organisms descend during day and rise at night. But extreme temperatures create another problem. Chemical reaction rates change with temperature, not just biological reactions, but all chemistry. At higher temperatures, dimethyl sulfide breaks down faster. At lower temperatures, it persists longer. The varying lifetime throughout the orbital cycle complicates atmospheric modeling. Scientists must account for time-dependent chemistry, where reaction rates shift as the planet moves along its elliptical path. There is evidence that life adapts to cyclic extremes better than constant extremes. Organisms can prepare for predictable changes. Before winter arrives, trees move nutrients into their roots and shed leaves. Before dry season comes, some fish bury themselves in mud and enter hibernation. The key is predictability. If the 33-day cycle repeats reliably, life could evolve responses triggered by environmental cues like changing light intensity or temperature. But temperature is not the only challenge this planet presents. What about the day-night problem? When a planet orbits very close to its star, gravitational forces reshape everything. The star pulls harder on the near side than the far side. This difference in pull, called tidal force, creates friction inside the planet. Over millions of years, this friction slows the planet's rotation. Eventually, the planet rotates at exactly the same rate it orbits. One side permanently faces the star. The other side faces eternal darkness. This is confirmed physics, observed throughout our solar system. Our moon is tidally locked to Earth. The same side always faces us. We never see the far side from Earth without spacecraft. Mercury is nearly tidally locked to the Sun, rotating 3 times for every 2 orbits. Most planets orbiting close to red dwarfs are expected to be fully tidally locked. The timescale depends on distance, planet mass, and internal structure. For this ocean world orbiting just 13 million miles from its star, tidal locking almost certainly occurred within the first few 100 million years. This is theoretical, but strongly supported by calculations. Tidal locking creates dramatic consequences. The day side receives constant starlight, never experiencing night. Temperatures there remain high continuously. The night side receives no direct starlight ever, remaining frozen. Between these extremes lies a twilight zone, a ring around the planet where the star hangs at the horizon. This terminator region experiences neither full day nor full night. It might be the only place with moderate temperatures. On Earth, day-night cycles drive weather, ocean currents, and biological rhythms. Plants photosynthesize during day and respire at night. Animals coordinate activity to circadian rhythms. A tidally locked world lacks these cycles. Life there would need to adapt to constant conditions, whether always light or always dark. The twilight zone might host the most diverse life, benefiting from both illumination and moderate temperatures. But atmospheric circulation changes everything. A thick atmosphere transports heat from dayside to nightside. On Earth, atmospheric circulation creates wind patterns, jet streams, and weather systems. On a tidally locked planet, circulation would be far more extreme. Air heated on the dayside would rise and flow toward the night side. Cold air on the night side would sink and flow back toward the dayside. The result is a planet-wide circulation cell, with winds potentially reaching hundreds of miles per hour. Computer models show that a thick hydrogen atmosphere could transport enough heat to prevent the night side from freezing completely. The day side might reach 100 degrees Celsius or more, but the night side might stay above freezing due to heat transport. This creates habitable conditions across much larger surface area than the twilight zone alone. The ocean itself would circulate, driven by temperature differences and wind stress. Warm water would flow from dayside toward nightside. Cold water would return in deep currents. However, constant illumination on the dayside creates photochemical challenges. Sunlight drives chemical reactions in the atmosphere. On Earth, these reactions reset each night when the sun goes down. Reactive molecules produced during the day get destroyed at night, maintaining balance. On a tidally locked planet, the dayside never gets a break. Photochemistry runs continuously. This could destroy biosignature gases before they spread to the night side, or it could create exotic chemistry impossible on Earth. The night side presents different challenges. With no sunlight, photosynthesis cannot occur there. Any life on the night side must rely on chemical energy rather than light. On Earth, deep-sea ecosystems near hydrothermal vents demonstrate that life can thrive without sunlight. Chemosynthetic bacteria extract energy from hydrogen sulfide and other chemicals. An entire food chain exists independent of photosynthesis. Perhaps similar ecosystems cover this planet's night side, fed by chemicals upwelling from below. Tidal locking also affects tidal forces themselves, with the planet always showing the same face to the star. Tidal bulges remain fixed in place. The ocean would have a permanent high tide on the dayside and night side, with permanent low tide at the poles. This creates standing wave patterns unlike anything on Earth. What if this entire biological interpretation is wrong? Scientists do not assume biology is the only explanation. They test alternatives. Over the past decade, multiple research teams have investigated whether dimethyl sulfide can form without life. The results complicate the picture. In 2024, one team published experiments showing that ultraviolet light can drive reactions between methane and hydrogen sulfide that produce small amounts of dimethyl sulfide. This is confirmed experimental data, replicated under controlled conditions. The experiments worked like this. Researchers filled a chamber with gas mixtures similar to what might exist on Hycean planets: hydrogen, methane, carbon dioxide, and hydrogen sulfide in various ratios. They sealed the chamber and exposed it to ultraviolet lamps, mimicking starlight. Over days or weeks, they sampled the gas and analyzed its composition using mass spectrometry. The results showed formation of several organic sulfur compounds, including trace amounts of dimethyl sulfide. The mechanism involves free radicals, molecular fragments with unpaired electrons. Ultraviolet light breaks apart methane, creating methyl radicals. These radicals can then react with hydrogen sulfide, which also breaks apart under UV light. Through a series of reactions, methyl radicals combine with sulfur to form dimethyl sulfide. The chemistry is complex, involving multiple intermediate steps, but it works. You can make dimethyl sulfide without biology. However, the yields were tiny. The experiments produced dimethyl sulfide at concentrations measured in parts per billion, To reach the parts per million levels observed on this ocean world requires yields thousands of times higher. The researchers acknowledged this limitation. They suggested that perhaps continuous volcanic outgassing of hydrogen sulfide combined with intense photochemistry might boost production, but even generous assumptions fell short of explaining observations. Another experiment explored different pathways. Scientists simulated conditions in molecular clouds, the cold, dense regions of space where stars form. They mixed simple molecules on ice grains and exposed them to radiation. Under these extreme conditions, they created various organic compounds, including dimethyl sulfide. This showed that dimethyl sulfide can form in space before planets even exist. Comets and asteroids might deliver dimethyl sulfide to planetary atmospheres during impacts, but delivery by comets faces problems. Any dimethyl sulfide delivered from space would be destroyed quickly by atmospheric chemistry. To maintain the observed concentrations requires continuous replenishment. A planet would need constant bombardment by dimethyl sulfide-rich comets. We see no evidence for such bombardment. Crater counts on planets and moons provide clues about impact rates. This ocean world, based on its age and orbit, should not experience heavy bombardment. A third set of experiments examined high-temperature chemistry. When hydrogen sulfide reacts with organic molecules at temperatures above 500 degrees Celsius, various sulfur compounds form. Volcanic vents on the seafloor might provide such conditions. Hot fluids rich in hydrogen sulfide, mixing with organic molecules from biological or abiotic sources, could generate dimethyl sulfide. This pathway does not require life directly, though it might require organic precursors that life produces. The challenge is scale. All these abiotic pathways work in principle. They produce measurable dimethyl sulfide in laboratory settings, but scaling them up to planetary levels requires extraordinary conditions. Constant intense UV radiation, massive volcanic outgassing rates, unusual atmospheric compositions that maximize production while minimizing destruction. The combination of all factors needed simultaneously seems unlikely, though unlikely is not impossible. One researcher put it bluntly, yes, we can make dimethyl sulfide without life. But making enough dimethyl sulfide to explain observations without life requires so many special conditions that invoking biology becomes simpler. Biology is efficient at producing specific molecules. Abiotic chemistry tends to produce everything at once in small amounts. The specificity and abundance of dimethyl sulfide points toward biological production. But what about false signals from space debris? In 2022, scientists made an unexpected discovery. They detected dimethyl sulfide on a comet. The comet, named 67P Churyumov-Gerasimenko, was visited by the European Space Agency's Rosetta probe. Instruments aboard Rosetta sampled the gas and dust streaming from the comet's surface as it warmed near the sunday. Among dozens of detected molecules, dimethyl sulfide appeared. This confirmed that dimethyl sulfide exists in cometary ice, created through abiotic processes before the comet formed. The detection challenged assumptions about biosignatures. If comets contain dimethyl sulfide, then finding it on a planet might not indicate life. Perhaps impacts delivered the molecule. Perhaps outgassing from deep within the planet releases cometary material that accreted during formation. Either scenario could explain atmospheric dimethyl sulfide without biology. This possibility is supported by direct comet observations, not speculation, but quantities matter. The dimethyl sulfide detected on the comet existed at very low abundance, parts per million in the comet's ice. When that ice sublimates into gas, it dilutes even further. Delivering enough dimethyl sulfide to explain atmospheric concentrations of 10 parts per million would require enormous numbers of impacts. Scientists calculated the required impact rate. The numbers were absurd. You would need impacts dumping thousands of tons of cometary material into the atmosphere every day. Such high impact rates would show other effects. impacts deliver more than just dimethyl sulfide. Comets contain water, carbon monoxide, ammonia, methanol, formaldehyde, and dozens of other molecules. If impacts were delivering dimethyl sulfide, they should be delivering all these other molecules too. Yet, atmospheric observations do not show unusual abundances of other cometary volatiles. Carbon monoxide appears absent or very low. Ammonia is missing. The chemical signature does not match continuous cometary delivery. There is another problem: impact speeds. When a comet hits a planet, velocities range from tens to hundreds of kilometers per second. These hypervelocity impacts release enormous energy. Temperatures at impact sites reach thousands of degrees. Most molecules get destroyed. Complex organic molecules like dimethyl sulfide would break apart into simpler fragments. Only the most robust molecules survive. Dimethyl sulfide is not particularly robust. It should be destroyed, not delivered intact. Some impacts occur at lower velocities. If the planet captures a comet gravitationally and the comet spirals inward slowly, it might hit at just a few kilometers per second. These gentle impacts might preserve molecules better, but gentle impacts are rare. Most comets either miss entirely or hit hard. The probability of sustaining continuous gentle impacts over millions of years seems vanishingly small. There is one scenario where cometary delivery might work. If the planet formed in a region rich with cometary material and captured huge amounts during formation, that material could be stored in the planet's interior. Over time, volcanic activity or convection might bring this material to the surface, releasing ancient cometary volatiles into the atmosphere. This would not require ongoing impacts, just release of primordial material. But this scenario requires the dimethyl sulfide to survive inside the planet for billions of years. Planetary interiors reach temperatures of thousands of degrees. Pressures exceed millions of atmospheres. Most molecules break down under such conditions. Only the most chemically stable compounds survive. Dimethyl sulfide would almost certainly be destroyed during storage. Water survives because it is extremely stable. Simple gases like hydrogen, methane, and carbon dioxide survive. Complex organic sulfur compounds do not. The comet connection remains a cautionary tale rather than a real alternative. It reminds scientists that biosignature molecules can have non-biological sources. It forces more careful interpretation of observations, but it does not explain the specific case of this ocean world. The dimethyl sulfide concentrations are too high. The lack of other cometary signatures is too complete. The chemical environment is too destructive to preserve delivered molecules long term. What about volcanic sources that mimic life's chemistry? Volcanoes on Earth spew sulfur in many forms. Sulfur dioxide dominates volcanic emissions, released when magma rises and pressure drops. Hydrogen sulfide follows, the rotten egg smell associated with volcanic regions. Sulfur's chemistry is complex, with multiple oxidation states, allowing it to bond with almost anything. In volcanic environments, sulfur reacts with carbon, hydrogen, and oxygen to form dozens of different compounds. This is well-established geochemistry, observed at volcanic sites worldwide. Could volcanic processes on this ocean world create dimethyl sulfide? One pathway involves methane, reacting with sulfur-containing volcanic gases. Methane is abundant in the atmosphere, confirmed at 1% concentration. If volcanic vents release hydrogen sulfide, and that hydrogen sulfide encounters methane under the right conditions, reactions could produce organic sulfur compounds. High temperatures would favor different products than low temperatures. The right temperature range might favor dimethyl sulfide formation. Laboratory experiments explored this possibility. Researchers mixed methane and hydrogen sulfide and heated them to various temperatures. At 500 to 700 degrees Celsius, various organic sulfur compounds formed. Carbon disulfide appeared, carbonyl sulfide appeared, methyl mercaptan appeared. Dimethyl sulfide appeared but only in trace amounts. The product distribution was messy, producing many molecules simultaneously. That is typical of abiotic chemistry. Life produces specific molecules efficiently. Abiotic processes produce everything at once inefficiently. The volcanic pathway faces quantitative problems. To maintain 10 parts per million dimethyl sulfide in the atmosphere requires continuous production, matching destruction rates. Scientists calculated the necessary volcanic outgassing rates. They estimated that hydrogen sulfide emissions would need to exceed Earth's entire volcanic output by factors of hundreds or thousands. This ocean world would need to be one of the most volcanically active bodies in the known universe. While not impossible, it seems unlikely. There is also the methane problem. Methane itself requires explanation. On Earth, most atmospheric methane comes from biology, produced by methanogenic bacteria or released during decomposition of organic matter. Some comes from geological sources like serpentinization, where water reacts with certain rocks to produce hydrogen and methane. But these geological sources produce relatively small amounts. The 1% methane on this ocean world exceeds what abiotic processes typically generate. If volcanoes produce the methane, they must also produce dimethyl sulfide through the same processes. That creates a self-consistent abiotic scenario, but it requires extraordinarily active volcanism and specific chemical conditions that maximize organic molecule production. Models struggle to achieve both requirements simultaneously. Either volcanism is too weak to produce enough gas, or temperatures are too high to allow organic molecules to survive. Another volcanic pathway involves intermediate water chemistry. Volcanic gases dissolve in ocean water. The dissolved gases then react with each other in solution rather than in the atmosphere. Aqueous chemistry allows different reaction pathways. Some reactions that do not work in gas phase proceed efficiently in water. Perhaps dissolved hydrogen sulfide and dissolved organic molecules combine to form dimethyl sulfide in the ocean. The dimethyl sulfide then evaporates into the atmosphere. This aqueous pathway faces its own challenges. Ocean chemistry is buffered by dissolved minerals. Seawater on Earth has a pH around 8, slightly alkaline. This pH range strongly affects what reactions occur. Dimethyl sulfide formation generally favors acidic or neutral conditions, not alkaline. But we do not know the pH of this ocean world's water. If volcanic activity acidifies the ocean, that might favor dimethyl sulfide formation. However, acidic oceans would dissolve carbonate minerals and show different atmospheric carbon dioxide levels. The observations do not clearly support extreme pH. The truth is that scientists have not yet found a volcanic pathway that fully explains the observations without invoking extraordinary conditions. Volcanic sources might contribute some dimethyl sulfide. They might explain part of the signal. But explaining the full observed concentration requires either extreme volcanism or highly specific chemistry, or both. As explanations go, biology remains simpler. What if the star itself makes this planet uninhabitable? Red dwarf stars are violent. They erupt with massive flares, releasing energy equivalent to billions of nuclear bombs. These stellar flares blast nearby planets with X-rays, ultraviolet radiation, and streams of charged particles. The flares happen frequently, sometimes multiple times per day during active period. This is confirmed through observations of thousands of red dwarfs. We have watched them flare. We have measured the energy. The danger is real. Why do red dwarfs flare so much? The answer lies in how they generate magnetic fields. Stars create magnetic fields through dynamo processes, where flowing electrically conductive plasma generates electric currents that produce magnetic fields. On our Sun, the dynamo operates in a shell near the surface. On red dwarfs, the dynamo operates throughout the entire star because they are fully convective. Hot plasma from the core rises to the surface. Cool plasma from the surface sinks to the core. This creates powerful, tangled magnetic fields. These magnetic fields store enormous energy. Sometimes field lines become twisted and stressed. When they release that stored energy suddenly, you get a flare. Material heated to millions of degrees erupts from the star's surface. Radiation across the electromagnetic spectrum floods outward. For a planet orbiting close by, this is catastrophic. The radiation hits in minutes. There is no warning, no time to take shelter. What does this radiation do to atmospheres? Ultraviolet light and X-rays slam into the upper atmosphere, ionizing molecules and atoms. Ionization strips electrons from atoms, creating charged particles. These charged particles are reactive. They tear apart molecules. Complex organic molecules get destroyed. On Earth, our magnetic field and thick atmosphere protect us from solar flares. Mars lacks a strong magnetic field and has a thin atmosphere, partly because solar wind stripped it away over billions of years. This ocean world orbits much closer to its star than Mars. Orbits the Sunday, the flares hit harder. The radiation is more intense. If the planet lacks a magnetic field, the atmosphere is exposed directly. Scientists estimate that over billions of years, a red dwarf could strip away several Earth masses of atmosphere from a nearby planet. That this ocean world retains its atmosphere suggests either it has a magnetic field, or its gravity is strong enough to hold onto atmosphere despite losses, or the star is less active than typical red dwarfs. Magnetic fields depend on planetary interiors. Earth has a magnetic field because its liquid iron core convects, creating a dynamo similar to stellar dynamos. Rocky planets with solidified cores lose their magnetic fields. This ocean world is massive enough that it might retain internal heat from formation. If it has a liquid metallic core, it could generate a magnetic field, but no observations directly confirm this. We cannot measure magnetic fields on such distant planets yet. We can only infer their presence or absence from indirect evidence. Even if a magnetic field exists, flares still pose problems for life. The radiation might not strip the atmosphere entirely, but it penetrates deep enough to affect surface conditions. On Earth, the ozone layer absorbs harmful UV radiation. Oxygen in the atmosphere creates ozone. This ocean world has minimal oxygen. Without ozone, UV radiation reaches the surface unimpeded. Organisms there would need protection mechanisms, like thick cell walls, radiation-resistant proteins, or simply living underwater, where water absorbs radiation. Flare frequency matters. If flares happen daily, life must cope with constant bombardment. If flares happen yearly, there are long recovery periods. Observations of this particular red dwarf show it is relatively old at 2.4 billion years. Old red dwarfs tend to be calmer than young ones. Stellar activity declines over time as stars spin down and magnetic fields weaken. Perhaps this star has mellowed enough that its flares no longer threaten planetary atmospheres severely. But even quiet red dwarfs flare occasionally. One massive flare could temporarily destroy biosignature gases in the atmosphere. If dimethyl sulfide gets obliterated during a flare, observations afterward would show lower concentrations. Multiple observations spread across months would reveal whether concentrations vary with stellar activity. So far, the data comes from just 2 observation windows. More observations might show temporal variations that reveal flare impacts. What about the gentler but persistent stellar wind? All stars emit stellar wind, streams of charged particles flowing outward. Our sun produces solar wind that travels about 1 million miles per hour. This wind carries away mass. Over the sun's lifetime, it has lost a tiny fraction of its total mass through this process. The wind also carries magnetic field lines that interact with planetary magnetic fields. Earth's magnetosphere deflects most solar wind around us. Particles that penetrate create auroras at the poles. This is well understood space physics, confirmed by decades of spacecraft measurements. Red dwarf stars emit weaker stellar winds than the Sun by total mass loss. But their planets orbit so close that wind density becomes important. Imagine standing in a gentle breeze versus standing in that same breeze while pressed against the fan producing it. This ocean world sits 13 million miles from its star. Earth sits 93 million miles from the Sunday. The planet orbits 7 times closer relative to stellar size. At that distance, stellar wind density is significantly higher. Stellar wind erodes atmospheres through several mechanisms. First, momentum transfer. Fast-moving particles collide with atmospheric atoms and molecules. Sometimes these collisions impart enough energy for atmospheric particles to escape gravity. This is called sputtering. One by one, atoms get knocked into space. Over millions of years, sputtering removes substantial atmospheric mass. Second, charge exchange. Stellar wind consists of ionized particles, mostly protons. When these ions encounter neutral atoms in an atmosphere, they can steal electrons. The newly ionized atmospheric atoms respond to magnetic fields. They get swept up by the stellar wind and carried away. This process is particularly efficient at removing hydrogen and helium, which are light and easily ionized. Third, atmospheric heating. Stellar wind deposits energy into the upper atmosphere. The atmosphere heats up. Hot atmospheric particles move faster. Some reach escape velocity and drift away. This thermal escape mechanism is most effective for light elements. Hydrogen escapes fastest. Then helium. Heavier elements like nitrogen, oxygen, and carbon escape more slowly but still escape. Mars provides a cautionary tale. Mars once had a thicker atmosphere, evident from ancient river valleys and lake beds. Over billions of years, solar wind stripped most of it away. Mars lost its magnetic field early in its history when its core solidified. Without magnetic protection, the atmosphere was vulnerable. Today, Mars has less than 1% the atmospheric pressure of Earth. The planet dried out and froze. This is confirmed by rover missions and orbiting spacecraft that measured atmospheric loss rates directly. Could the same fate befall this ocean world? The hydrogen atmosphere might actually help protect against loss. Hydrogen is the lightest element. It occupies the uppermost atmospheric layers. Stellar wind interacts primarily with this hydrogen, stripping it away but leaving heavier molecules deeper in the atmosphere untouched. The massive hydrogen envelope acts as a sacrificial shield. As long as the planet replenishes hydrogen from below, it can maintain atmosphere indefinitely. But where does replacement hydrogen come from? If the planet has a hydrogen-rich interior, convection and outgassing could release hydrogen continuously. Alternatively, if the planet contains water, that water could break down into hydrogen and oxygen. The hydrogen escapes. The oxygen reacts with surface materials or gets incorporated into molecules. This would slowly dry out the planet over billions of years. Venus demonstrates this process. Venus lost an ocean's worth of water through hydrogen escape. The planet baked dry under a runaway greenhouse. Scientists estimate atmospheric loss rates using models that input stellar wind properties, planetary gravity, magnetic field strength, if any, and atmospheric composition. For this ocean world, estimates vary widely depending on assumptions. Optimistic models suggest atmospheric loss rates low enough that the planet retains atmosphere for billions of years. Pessimistic models suggest rapid loss that would strip the atmosphere within hundreds of millions of years. The fact that atmosphere remains after 2 billion years provides a constraint. Loss rates cannot be as high as the pessimistic models predict, but beyond that conclusion remains uncertain. What about the crazy elliptical orbit? Remember the elliptical orbit. Eccentricity of 0.09 means the planet's distance from its star varies by 12% between closest and farthest approach. That translates to 43% variation in received starlight. Imagine if Earth's seasons worked that way. Instead of gentle temperature changes driven by axial tilt, we would experience violent swings every few months. This is confirmed orbital mechanics, calculated directly from precise timing measurements of transits. The orbital period is 33 days. That means the planet goes from maximum starlight to minimum starlight in about 16 days, then back to maximum in another 16 days. For life, this creates a punishing rhythm. Just as organisms adapt to high temperatures and high light levels, conditions reverse. Temperatures drop, light dims. Then, before adaptation completes, conditions reverse again. It is like trying to acclimate to summer and winter simultaneously. On Earth, seasonal changes happen slowly enough that life adapts. Trees sense day-length changes months before winter and prepare by moving nutrients and shedding leaves. Animals build up fat reserves or migrate to warmer climates. These adaptations work because seasons last months and repeat predictably every year. But 33-day cycles are faster than most biological adaptations. A tree cannot grow leaves, then shed them, then grow them again every few weeks. Microbial life might handle this better than complex organisms. Bacteria reproduce quickly. Generation times can be hours to days. In 33 days, bacteria go through dozens or hundreds of generations. That allows rapid evolution. Bacterial populations could adapt to changing conditions through natural selection operating in real time. Beneficial mutations spread through the population within one orbital period. Complex organisms with generation times of years cannot adapt this quickly. The temperature swings affect ocean circulation. Warmer water expands, cooler water contracts. As the planet moves through its orbit, the ocean literally swells and shrinks. This creates tides separate from gravitational tides. These thermal tides would drive currents, mixing surface and deep water. The mixing might help distribute nutrients, benefiting marine life, or it might disrupt stable water layers, harming organisms adapted to specific depths. Atmospheric chemistry changes with temperature too. Chemical reaction rates double every 10 degrees Celsius, as a rough rule. If surface temperatures vary by 20 degrees over the orbital cycle, reaction rates vary by a factor of 4. Dimethyl sulfide destruction happens 4 times faster at orbital closest approach than at farthest approach. Production rates also vary if they depend on temperature-sensitive biological processes. The result is that atmospheric concentrations might oscillate with the orbit. Webb observations captured snapshots at specific moments during the orbit. The data represents whatever conditions existed when the planet happened to transit its star. If concentrations vary significantly, different observations might show different dimethyl sulfide levels. Comparing multiple observations could reveal whether concentrations are stable or variable. So far, 2 observations show consistent results. But 2 data points are not enough to rule out variability. The elliptical orbit also affects the habitable zone concept. Traditionally, the habitable zone is defined as a distance range where a planet with Earth-like atmosphere maintains liquid water. That assumes circular orbits. For elliptical orbits, the planet spends part of each orbit inside the traditional habitable zone and part outside. This ocean world swings from just inside to just outside the habitable zone with each orbit. Whether liquid water can persist under such conditions depends on how quickly the ocean responds to changing conditions. Water's high heat capacity provides buffering. Oceans do not heat up or cool down instantly. They lag behind atmospheric changes. Even if air temperatures swing dramatically, ocean surface temperatures might vary by just a few degrees. Deep ocean temperatures might barely change at all. Life could exist in these more stable deep layers, protected from orbital variations. Alternatively, life could migrate vertically following optimal temperature layers as they move up and down. What must future observations confirm to settle the debate? The next observations must separate dimethyl sulfide from dimethyl disulfide. Current data shows absorption features consistent with either molecule or both. They are chemical cousins with similar spectral signatures in the observed wavelength range, but they are not identical. Expanding observations to longer wavelengths would reveal differences. Dimethyl disulfide has strong absorption features between 6 and 7 microns. Dimethyl sulfide does not. Observing at those wavelengths would determine which molecule is present. This matters because dimethyl sulfide and dimethyl disulfide form through slightly different pathways. On Earth, dimethyl sulfide comes primarily from phytoplankton breaking down dimethyl sulfoneopropionate. Dimethyl disulfide comes primarily from bacterial metabolism. Finding one versus the other versus both would constrain what types of organisms might exist. All are biosignatures, but they tell different stories about the ecosystem. The observations must also increase statistical significance. Current confidence sits at 3 sigma, 99.7%. That means 0.3% chance of error. Science demands 5 sigma for discovery, which drops error probability to 0.00006%. Achieving 5 sigma requires more observation time. Each additional transit observation improves the signal-to-noise ratio. With 2 or 3 more transits, scientists estimate they would reach 5 sigma. 5 sigma is not arbitrary. It is the threshold where chance becomes so unlikely that systematic errors become the main concern. At 3 sigma, you might see a pattern by luck. At 5 sigma, luck is essentially ruled out. Any remaining uncertainty involves whether the instruments are calibrated correctly or whether the models are complete. Those questions can be addressed through independent verification and alternative analysis methods. Independent verification means other teams analyzing the same data. Scientific results gain credibility when multiple groups reach the same conclusion using different analysis techniques. Web data is public after a short proprietary period. Anyone can download it and analyze it. Multiple teams have already looked at the dimethyl sulfide signal. They generally agree it is real, though debates continue about interpretation. More data would give more to analyze and would help resolve disagreements. The observations should also search for other biosignature candidates. Methyl chloride is predicted to be a biosignature on Haitian worlds. It forms when organisms incorporate chlorine into organic molecules. Earth's oceans contain methyl chloride produced by marine algae and kelp. Finding it on this ocean world would provide independent evidence for biology. Conversely, not finding it might suggest abiotic processes dominate. Oxygen remains the gold standard biosignature. On Earth, photosynthetic organisms produce oxygen as waste. It accumulates in the atmosphere because constant replenishment overcomes chemical destruction. Finding oxygen on an exoplanet would be powerful evidence for life, though abiotic oxygen production is possible through water photolysis. This ocean world shows no oxygen, which actually fits the Haitian hypothesis. Hydrogen atmospheres would not accumulate oxygen even if organisms produced it. The hydrogen would react with oxygen immediately. Seasonal variations deserve attention. If biosignature concentrations change over time, that might reflect biological cycles, orbital variations, or stellar activity effects. Earth's atmosphere shows seasonal cycles in carbon dioxide as plants grow and decay. Similar cycles on another world would suggest biology responds to environmental changes. Alternatively, stable concentrations over months or years might suggest robust equilibrium between production and destruction. The ultimate goal is not just confirming dimethyl sulfide presence, but understanding its source. That requires detecting a suite of molecules that together point unmistakably to biology or clearly indicate abiotic processes. No single molecule proves life exists, but combinations of molecules that only make sense together with biological production would be compelling. What threshold must we cross before declaring we have found alien life? The stakes could not be higher. Announcing the discovery of alien life would be one of the most profound moments in human history. It would answer a question we have asked for thousands of years. Are we alone? The answer would reshape philosophy, religion, science, and our sense of place in the universe. Getting it wrong would be catastrophic. Claiming life exists when it does not would destroy credibility. Future genuine discoveries might be doubted. That is why scientists demand 5 sigma certainty. 5 sigma means the probability of being wrong through random chance is less than 1 in 3.5 million. That is like flipping a coin and getting heads 22 times in a row. Possible, but so unlikely you would bet everything that the coin is rigged. In particle physics, 5 sigma is how scientists confirmed the Higgs boson. In astronomy, 5 sigma is how gravitational waves were announced. For alien life, anything less would be irresponsible. This is not official policy, but rather scientific consensus built through hard experience. History teaches caution. In 1996, NASA scientists announced possible fossilized bacteria in a Martian meteorite. The news made headlines worldwide, but further analysis revealed alternative explanations. What looked like bacterial fossils might be mineral formations. What looked like biological markers might be contamination. Today, most scientists consider the evidence insufficient. The episode taught everyone involved to demand stronger proof before making bold claims. More recently, phosphine on Venus generated excitement. In 2020, scientists reported detecting phosphine gas in Venus's clouds. On Earth, phosphine is produced by bacteria or industrial processes. Finding it on Venus suggested possible microbial life floating in the clouds, but reanalysis questioned the detection. The spectral signature might actually be sulfur dioxide misidentified. The claimed phosphine might not exist at all. Confidence eroded from strong detection to uncertain maybe. Those false starts had consequences. Public interest in astrobiology remains high, but skepticism increased. Media outlets treat new claims more cautiously. Scientists face pressure to be absolutely certain before going public. The dimethyl sulfide discovery comes with those lessons learned. The research team repeatedly emphasizes caution. They are not claiming life has been found. They are claiming a biosignature that requires explanation. The difference matters. A biosignature is a signal consistent with life. It is not proof of life. Other explanations might exist. The signal might be misinterpreted. The observations might contain errors. Only after exhausting alternatives and confirming the signal repeatedly can scientists consider claiming discovery. That process takes time. It requires patience. It requires additional observations that might take years to obtain. Public communication challenges this approach. The moment preliminary results suggest alien life, media coverage explodes. Headlines simplify complex findings. Nuance gets lost. The public hears that scientists found aliens when scientists actually said they found a signal that might indicate life. Managing expectations becomes crucial. Overclaiming causes backlash. Underclaiming means discoveries get ignored. Finding the balance is difficult. Some argue that 5 sigma is too strict for biosignatures. Unlike particle physics, where experiments can be repeated easily, astronomical observations depend on limited telescope time. Waiting for 5 sigma might take decades. Meanwhile, the signal is real. Should society wait for perfect certainty before acknowledging probable discoveries? Others counter that premature announcements cause more harm than delays. Better to be late and right than early and wrong. This ocean world exists at that threshold. The signal is strong. The interpretation is reasonable. Alternative explanations struggle to explain observations, but doubt remains. Maybe something unexpected is happening. Maybe the models miss important chemistry. Maybe multiple coincidences align to mimic a biosignature. Reaching 5 sigma would not eliminate these possibilities completely, but it would push them into implausibility. The next year will be crucial. If additional observations reach 5 sigma, and if alternative explanations continue to fail, the scientific community will face a decision. At what point does probable become definite? At what point do we accept that we have detected life beyond Earth? That decision will not be made by one person or one team. It will emerge from consensus across the entire field of astrobiology. We stand at the edge of knowing. 124 light-years away, a planet orbits a dim red star. Something in its atmosphere creates chemicals that on Earth only life produces. Something is happening there that we cannot yet explain without invoking biology. The telescope stares. The observations accumulate. The certainty builds. Within months or years, we will know whether this ocean world is inhabited or whether we fooled ourselves again. Either way, we have entered a new era. The era where finding life elsewhere is not a fantasy, but a scientific question with real data and real answers approaching. The question that has haunted humanity since we first looked at stars may finally be answered. We are close, so very close.